Everyone, this is GR3D for Physics 110. In the last video, we covered parts A and B of workout problem 1. I'm going to finish it out with C and D in this video. Hopefully these won't take as long as A and B. They're a little bit shorter. So let's look at part C. Next, the kid walks from point P to the very edge of the rotating merry-go-round. What is the new angular speed of the rotating system when she gets there? If you haven't read this question yet, or you don't know what's going on, I would suggest watching the previous video so you can get the context behind this question and the math we already did in parts A and B, so you're not completely lost when I bring up stuff from the last video. So in this question, so the kid is already on the merry-go-round, so we're starting, we're pretty much starting at the end. We don't have to worry about her being over here anymore because she's now on the merry-go-round. Now she's walking from the point she's at to the point P on the very edge of the rotating merry-go-round. And they're asking for the new angular speed. So, let's see. Yeah, so she starts at point P when she jumps on the merry-go-round. And she walks, while it's still spinning, to the edge of the merry-go-round. And it wants to find the new speed. So with this one, let's see here. So we have... let's see what equations we can use. So in this one, I chose to use conservation of momentum. I don't know if there's another way that you could do it, but it seemed most reasonable to me because I was looking at when it says we're trying to find the new angular speed. In other words, we're trying to find omega final when she gets to that final point. And the only thing that's changing is the distance she walks from point P to the edge of the circle. And so the only thing that's changing is her distance from the center of the circle. In other words, her moment of inertia. Because if you remember in parts A and B, when we calculated I of the kid, we used the radius of her current position to the center. So if she's the only thing that's changing in this problem is her position, then the only thing that's changing in this problem is the I of the kid. So, that's why I chose to use conservation momentum, because we know whatever our initial L was is gonna equal our final momentum. So, if we plug in some numbers here, we get I omega equals I omega, but we know it's not just I, because in parts A and B we saw that we have to take into account if I has to count for both the merry-go-round and the kid, or one or the other. In this case, the kid is on the merry-go-round the entire time. So our I in both of these initial and finals will be I of the merry-go-round plus I of the kid. So I'm going to write that out. Plus I of the kid. Omega final. Okay, so let's plug in some numbers. So we got IM, that's always given to us, is 140. The I of the kid, remember when she's at point P, that's just the same I that we used in part A and part B, and we just used it as an MR squared. And so, here, I'll write that out. I of merry-go-round plus MR squared, just so we don't get confused. I of the merry-go-round plus MR squared. Now we'll plug in some numbers. So 140, mass of the kid is 35. The radius in this case is not the radius of the entire circle because she's at point P, which it gives it to us as R over 2 squared. To visualize that, I'll go back to our image. So when she jumps on it, she's at point P, which is at a distance R over 2 from the center, not a distance R. So that's where we plug R over 2 into that R. And then our omega initial, be careful you don't use this omega initial. It might be tempting to say, oh, omega initial, that's 0.45. But we have to consider what are we calling our initial position. Our initial in this case is when she's already on the merry-go-round at point R over 2. And so our omega in that case would be whatever the angular speed was after she jumped on it. And so if we look back at what it gave us, in part A it said the final angular speed after the kid lands is 0.75. So that is our omega initial, not our not that original, very, very original 0.45. So make sure you keep those straight. So then we got on this side, we have a 140. Oh, I'm sorry, I forgot parentheses. That's a sum and then a multiplication. This side we have a 140 plus 35. Now in this case, this is where the R comes in, because as she walks from point R over 2 to the outer edge of the merry-go-round, her radius is now the radius of the merry-go-round, which I guess I could have plugged in numbers earlier, but the radius is 1.7. So here we have a radius of 1.7, and I'm going to go over here and turn this R over 2 into our 0.85, because that's 1 over 7 divided by 2. Okay, so R squared, 1.7 squared, and then our omega final. And remember, that's what we're trying to find, is her omega final. So that's good. We have every number accounted for, and we only have one unknown as omega final. So now it's just plug into the calculator, solve for omega. Again, if you're the kind of person that wants to solve symbolically for omega first before you plug in numbers, go for it. I just chose to plug them in and then do the algebra, but whatever works for you on the test. So if I plug in some numbers here, omega final, I got 0.514 radians per second. Okay, last part is part D. This one should go pretty quickly. What is the tangential speed of the kit at the edge of the rotating merry-go-round? So whenever it asks for tangential speed, this is now referring to V instead of omega. Whenever you see angular speed, that's omega. Tangential speed is V. So we figured out our omega final in part C, and now it's just asking for tangential speed at the edge of the rotating merry-go-round. So all we have to do is reference our one equation that says V equals omega R. I don't think your equation sheet writes it as V over R, but either way, both of these will give you the right answer, because when we plug in our omega and our R, we're just left with our V. So V equals our omega that we just calculated, so 0.514, times our radius of 1.7 meters, and our final V is 0.874 meters per second. And that's it for workout problem 1.